welcome everybody to this webinar. So today topic is going to be the 3D mastering for nanoimprinting and injection molding. If you have been following our webinar series, you are aware of that NanoFrazor is a very good instrument for patterning very high accuracy 3D topographies in the resist. That is thanks to the closed loop lithography principle and the advanced feedback algorithms that are integrated in the software. So we can actually achieve, for example, sine waves or this kind of checkerboard structure, actually any arbitrary grayscale pattern with sub 1 nanometer accuracy. And today I'm going to discuss how to actually transfer this into other materials, but actually with a special focus on more higher volume transferring, so towards high volume manufacturing, more industrial applications. Now the approach that we have been studying the most is nanoimprint lithography, or NIL in short. In this approach, we use the existing 3D topographies as a stamp, or as it's called a master in the jargon of the field. So we can, for example, take our 3D pattern that we just wrote with a NanoFrazor, for example, the sine wave, and then we spin coat a resist on our target substrate, be it a silicon wafer, it can be a glass slide or a quartz substrate, whatever. We align the stamp where we like to make the imprint, and then we press them together. So of course, if you want to press the stamp into the resist has to be either heated up above its glass transition temperature, or it has to be in a liquid form. And finally, the resist is either cured or it is cooled down, and we can then demold the substrate from the master. And actually, important detail is that we always have a residual layer of resist remaining between the stamp and the substrate. And this is for the sole purpose of preserving the stamp from any damage, mechanical damage that may occur if it's actually pushed towards a hard substrate. So we can actually, the idea is that we can use the stamp as many times as possible to replicate as many copies of it as possible. So what is super nice about this technique is that it's capable of both 2D and 3D replication. And it is actually the resolution is limited only by the resolution of the stamp. That is the main limiting factor here. And also the master size is defining the throughput. The larger original master we have, the faster we can also replicate these structures. And it is in fact has been gaining attention as an alternative to common high resolution lithography techniques such as E-beam, EUV lithography, or even a focused ion beam. But actually you still need these traditional techniques for fabricating the masters. There's no way around it. Now we have been working with three different companies, three different providers of nanoimprint lithography processes. I will first present the Austrian EVG process, their SmartNIL process. This was a part of a European Union project, SNM, single nanometer manufacturing process that ended a couple of years ago. So what we did, we first patterned a PPA master. So in this case, the master was just our thermal resist PPA. And we sent them to Austria for the processing, where they produced the working stamp by molding the working stamp material and by attaching a transparent backplate on it. And it was just peeled off mechanically to replicate to create a negative image of the original patterns. In the next step, the stamp was pressed against the NIL resist, and the UV light is exposed through the transparent backplate in order to cross-link the resist and to make an impression into it. Now, what is really nice about the EVG process is that their tool, the EVG Hercules, can actually carry out a step and repeat of the process. So what you can do, you can first create one replica of the stamp, and then you can move it to the following position, and you can make another replica just next to it. And you can, in a way, overcome the limitation of the master patterning speed by creating several replicas of the master on the same substrate. So you're not limited so much by the small area of the original master. We sent them test structure where it was made on a 4-inch silicon wafer, 50 by 50 micrometer area, 8-level holograms, resist thickness 100 nanometers, and the target pattern depth 64 nanometers. The target structure is seen here on the left, and the actual structure written in the PPA is seen on the right. From the AFM images, we can see that the depth of the pattern corresponds very well, the target depth, and it is also uniform throughout the entire pattern. As I said, we sent the sample to EVG for replicating, and actually what they made, they made 10 of masters, so 10 working stamps out of this. And then they measured the 10th imprint and compared the AFM image of that to the original master. And they could practically see no degradation of the depth of the pattern, so it is pretty much the same. And also they could see no roughening or degradation of the pattern, even though just PPA was used to produce the replicas. Even if PPA is in no way optimized for nanoimprint master production, it seems to work quite nicely to this application. So next example I would like to show is something we did together with the company Skill, a Dutch company. So actually the company name Skill comes from the word substrate conformal imprint lithography. And indeed, that's what is special about their process. So they are using a double layer PDMS, first very thin cross-linked PDMS layer for replicating the topography of the substrate. Then they use a soft PDMS intermediate layer, and then a very thin glass slide handle wafer, kind of a handle substrate. Actually, the glass is so thin that the entire stamp conforms to non-smooth curved substrates, and also can be used for up to 300 millimeter wafers. So in this case, we have used a 2D pattern. So we have just made some very high resolution the structures to test the maximum resolution that we can achieve. And actually, we were able to reproduce these 12.5 nanometer wide lines very accurately to the imprint here. And actually, they are using a special sol gel resist for their process. The third example we did with micro resist technology, a German resist manufacturer. With them, again, we tried something else. So we wanted to make the stamp not out of PPA, but actually transferred to a silicon substrate in an effort to make it more durable, maybe. So we could make more replicas out of the same master. So here we have used the sine wave structure as the target pattern. We have first written it 70 nanometer deep in polymer, and as we can see here on the right, the target depth, the blue, is corresponding very well with the actual written depth shown in red. Then we have transferred the 3D topography into a silicon substrate using a standard reactive ion etching process, SF6 and C4F8 gases. And as a final product, we get a silicon sine wave 250 nanometers deep, corresponding to amplification in depth by a factor of 3.6. And here we can see a little bit tilted the image of the surface of the stamp. There are a couple of small particles here because it was not patterned in a clean room environment, but in fact just in an office environment. Next, the working stamp was fabricated using the Ormo stamp material by simply casting the Ormo stamp and again pressing and curing it with UV light through a transparent backplate and by demolding the working stamp. And here we can see an SEM image, which it's of course a negative image of the original silicon pattern, but we can see very nicely reproduced the couple of particles that we saw earlier. They are also reproduced here very nicely. So it's a very conformal technique. And finally, to fabricate the final imprint into the Ormo clear material, which is optical grade polymer that is used in, for example, laser waveguides, these kind of structures. The Ormo clear was coated on the substrate, and the stamp was pressed against it and cross-linked using the UV light, resulting in the final replicas that we can see on the right. And again, we can see very nicely reproduced every single, even unwanted detail of the original master structure. Again, comparing these all three side by side, the master template, the working stamp, and the imprint, at least I'm having a hard time telling apart the master template from the imprint. If I wouldn't know which one is which, I would be very hard pressed to tell you which one is which, because also even the tiniest little detail is reproduced in the final imprint. Now, what is then the one of the limitations? First of all, let's have a look at the maximum depth that we can achieve in these structures. How deep patterns can we expect to reproduce using the nanoimprint process? To understand this a little bit, let's have a look at first how the tip of our cantilever looks like. And in particular, if you look at it from the side, we can see that the extremely sharp tip is not situated exactly at the nose of the cantilever. And this is because of the way the resistive heaters are designed and built. So there's a couple of micrometer offset between the tip and the end of the cantilever. And also because we want to approach the substrate with a small angle, just to make sure that we always hit the substrate surface with the tip of the sharp tip first, not any other part of the cantilever. We apply a small angle, and from this geographical consideration presented here, we can see that actually the maximum patterning depth we can achieve in the PPA resist is well, it's not more than 250 nanometers in any case. And that's also we can etch the structures into silicon to achieve a little bit the deeper patterns. But the PPA selectivity against silicon is in the range of typically 3 to 5, and with some super nicely optimized process, we can achieve maybe amplification in the range of 10, but not much more than that. So that gives us a maximum pattern depth in the range of few micrometer. If we want to reach patterns that are deeper than that, we can follow a procedure suggested by our customers at EPFL. They actually introduce an intermediate hard mask layer just below the PPA, and they transfer the PPA patterns first into the silicon dioxide, for example. That could be the hard mask material. And then they use the silicon dioxide to etch the structures further into the silicon substrate. Again, everything is done using standard reactive ion etching processes. Just selectivity between the silicon dioxide is against silicon is much higher than the selectivity of PPA against silicon. Using this approach, they have been able to amplify the originally 35 nanometer deep structures in PPA into 4 nanometer deep structures in the silicon, corresponding to depth amplification by a factor of more than 100. And then, therefore, using this approach, we could imagine having structures in the range of hundreds of micrometers, even. Now, also sometimes it is desired to have the masters out of metal to make them even more durable. And in the previous webinar last week, I have shown how to fabricate metal replicas using the template stripping approach. In this process, first we have the 3D pattern in either the resist, or it can be transferred in silicon. After that, a very thick layer of metal, in this case 750 nanometers of silver, is evaporated on top. And finally, a glass slide is attached at the back using an epoxy glue adhesive. Once the epoxy is cured and dried, we can just mechanically strip away the metal film together with the glass slide, and we have an exact replica of the 3D structures as seen here in this SEM image. And as I can be seen here again, we are able to reproduce the topography very accurately using this approach. Another way of creating these metallic masters is the electroplating. Here first, the structures in PPA are coated with a seed layer, metal seed layer, and the sample is immersed in electroplating solution, where we can electroplate a metal on it of desired thickness. We could imagine, for example, nickel, but of course, why not gold, copper, for example, as well. And at the end of the process, we can apply, for example, the template stripping approach, so we can glue a backplate on the metal film, and we can remove the PPA by solvent or just by heating it up to decompose it. Here's an example structure, the topographical map of Switzerland that was first written with NanoFrazor, and then nickel was electroplated on top, and we can see a very nice reproduction of the mountain tops and all the valleys of Switzerland in this. Now, this kind of metallic templates could be very useful for another mass fabrication process, namely the injection molding, which is an very broadly applied industrially for replication of precision plastic parts. For example, I don't know, toys or medical devices, and this kind of every day a little bit nicer, more accurate plastic parts. So how it works, there is a cavity, and into the cavity you need to insert the insert, which has the negative of the topography you want to reproduce, and then you bolt all these parts together, and then you inject into the cavity molten polymer with high pressure and of course high temperature, and then you use these springs to open this apparatus up, and the polymer replicas come out from the other end. Really the volume for the fabrication can be tens of thousands, even hundreds of thousands of units per day, and this is therefore very high volume fabrication. Now, working together with the University of Applied Sciences in Northwestern Switzerland, we have used the process to make replicas of the nickel master template of the Swiss topographical map, not for any particular application, but just to show that the process can be used. And actually here on the bottom right, we can see the AFM image of the final plastic structure. And actually, given the extremely high volume of the process and the relative simplicity of the structure, it is quite impressively accurate representation of the master. Now, finally, the obvious question is that as I have presented technologies for high volume manufacturing, so what is actually the speed, the patterning speed to fabricate such masters? So actually, practically the throughput at very high resolution to create masters with a NanoFrazor is about 1,000 square microns per minute. And this, of course, includes the topographical AFM image that we get as a side product of the patterning process. And actually, when we compare this with the alternative technologies, such as focused ion beam or electron beam lithography, it is pretty much on par, so it is comparable. Since electron beam lithography requires resists like HSQ, which is a silicon-based resist that requires extremely high exposure dose for patterning such high resolution structures, and therefore the scanning speed with the beam is limited to less than 1 millimeter per second. But yes, we do realize that 1,000 square micrometer patterning speed is not it's not sustainable for fabricating say 4-inch wafer scale master, or even 1 by 1 centimeter would take a long time. But we are working towards increasing the throughput of the technology, and one way to do that is to introduce the multi-tip principle. So we have actually already demonstrated the use of these linear arrays of 10 tips for patterning, and the commercial version for testing. So for some selected beta customers will start using this already maybe end of this year. That's our target. And looking more into the future, we also have plans to introduce the NanoFrazor Professional, which can actually use sample substrates up to 8-inch wafer or even larger if there's a clear demand for that. This will of course introduce the multi-tip patterning and imaging, and also incorporate a high-speed laser writer for fabricating the lower resolution parts that are where the accurate 3D patterning is not required. For example, interconnects or something like that. And also the idea is to make it fully automated with automated chip and sample exchange modules. But as I said, it's not yet on the market. But if you are interested in buying one, get in touch. Okay, so to conclude, so I've shown that NanoFrazor can be used for making very high resolution masters for nanoimprint lithography, and high quality replicas can be produced out of them. The masters are compatible with scalable and commercially available nanoimprint lithography replication. So as I showed, we have worked together with 3 companies, and with all of these, we had no major complications regarding the processing and compatibility of materials or processes with what we are doing. Also, the TSPL patents, they can be transferred into silicon substrates or even metal to prolong the master lifetime. And also the metal masters can be used also for very high volume manufacturing by the injection molding approach. And also the NanoFrazor recipe book that was already mentioned, it contains much more detail on pattern transfer and replication processes as well. Thank you very much for listening.